Hello and welcome to all to this lecture series on fluid mechanics. This is lecture 2, basic concepts continued. In the last lecture we have seen some of the properties of the fluid and some more remaining properties are there. Let us do them. Property vapor pressure. What is that? If there is a container in which there is a liquid and it's basically a closed container and there is some space left above the free surface of the liquid, then the vapors from this liquid will get collected in this space between the free liquid surface and the top of the container, and these vapors will exert a partial pressure on the free liquid surface. This pressure is known as vapor pressure. Okay, so this is a container, there is liquid kept in it with the free liquid surface, and this is a closed container, so this part is empty. In this part the vapor from this liquid gets collected, and these vapors exerts the partial pressure on this free liquid surface, and that is known as vapor pressure, denoted by PV. Okay, and as the temperature increases, the vapor pressure will increase, because as the temperature increase, more amount of vapor will be generated, and more amount of vapor generated means the partial pressure exerted will be more. So as the temperature increases, vapor pressure will increase. Another property, compressibility, denoted by beta, and elasticity, denoted by K. This elasticity, or simply it is also known as the bulk modulus of elasticity, denoted by K, is the ratio of volumetric stress to volumetric strain. Okay, this K, volumetric stress by volumetric strain. See, if there is any volume and if we apply some pressure, so that change in pressure, that is the applied pressure, or that change in pressure is the volumetric stress, and the change in volume per unit original volume, that is the volumetric strain. So this is the formula, minus V dP by dV, where this V is the original volume, dP is the pressure, that is the volumetric stress, and dV is the change in volume. This formula is known as elasticity or bulk modulus of elasticity. Then what is compressibility? It is the reciprocal of bulk modulus of elasticity, beta, equal to 1 by K, which is equal to minus of dV upon V dP. Okay, then we have this thing that is known as mass. Mass is, you know, that density into volume, and that is constant. So on differentiating, what we will get, P dV plus V dP, sorry, this is not P, this is rho dV plus V d rho is equal to 0, or like this. On simplifying, you can get dV by V is equal to minus d rho by rho. So in the formula of K, where we have got dV by V, in this place we can substitute it with minus d rho by rho, so we can get K is equal to rho dP by d rho, and beta, that is 1 by K, that is d rho upon rho dP. So if d rho is equal to 0, then beta is 0. That means d rho 0 means it is an incompressible fluid, change of density is negligible. That means for incompressible fluid, rho does not depend upon pressure, because d rho becomes 0 and beta becomes 0 for incompressible fluids. Then one more condition is there for the incompressibility. If the Mach number, what is a Mach number? Mach number is the ratio of under root of viscous force by elastic force, okay, if that we will take in detail in the chapter of dimensional analysis later on, but for the time being you just sorry, take a note it in this way, that Mach number, when the Mach number is less than 0.2 to 2.3, then the variation in density is less than 5%, and variation in density is less than 5%. That means that in such cases even the gases can be assumed to behave as incompressible. That means the change in density can be considered to be negligible. Okay. Sorry. Then another property known as surface tension. It is the property by which the liquid tends to minimize the surface area, and it is because of the force of cohesion that the surface tension comes into existence. This question is asked time and again, that which force is responsible for the property of surface tension. That force is force of cohesion, and force of cohesion, I already told you, is a force between two substances or two matter of similar kind. If the force is between two different kinds of material, that is known as a force of adhesion. That is different from force of cohesion. Okay. The surface of the liquid droplets act like a stretched elastic membrane under tension, and the pulling force that causes this tension is due to the force of cohesion, and it acts parallel to the surface or along the surface. See, if this the intensity of these pulling forces per unit length is termed as surface tension. It is denoted by sigma, that is given by F by L, where this F is this pulling force and this L is the length. Unit is Newton per meter. Also, if we multiply and divide the numerator and denominator by delta L, so sigma can also be written as F into delta L upon L into delta L. This becomes delta W. Delta W means change in work, or this is L into delta L is change in area. This comes in the terms of work done per area, per unit area. The surface tension can also be defined as the surface energy. In this case, it represents the amount of work to be done for increasing the surface area by unit amount, because this is also sigma. Sigma can be written as amount of work to be done for increasing the surface area by unit amount. So this is also the one interpretation of the surface tension. Then how comes this force of surface tension originate? See, if this is a whole container having liquid, and if we consider two droplets of water, let us say one is droplet A, which is in the bulk of the container at the middle portion, surrounded by fluid from all the side, and this is droplet B, which is at the surface, okay, which is surrounded from liquid on these sides and which is not surrounded by liquid from the upper side. Okay, so in case of A, we will see that the forces are equal on all the sides. So this is basically subjected to symmetrical forces on all the sides. But whereas in case of liquid droplet B, they are not subjected to symmetrical forces. There is a resultant downward pull in this direction. So and there will be so many liquid droplets on this free liquid surface, in which all will experience a force in the downward direction. So this free liquid surface will behave as a elastic membrane in tension, and this causes the liquid to minimize the surface area, because all the forces are tending towards downwards and they are trying to pull this free liquid surface towards downward. So it acts like a membrane in tension, and due to this it looks as if these forces are trying to minimize this area of the liquid. Okay, so hence because of this case only, the liquid drops become spherical, as for a given volume a sphere has the minimum surface area. Why the liquid droplets that fall are always spherical? The reason is because of this surface tension, because liquid drop has a spherical shape, because sphere has the minimum surface area for a given volume. This is the reason why the liquid droplets are always spherical. Okay, then we have excess pressure intensity. See, inside a liquid droplet, this is a liquid droplet of radius r, and when it is cut into two halves, it becomes something like this. The pressure P is towards inside and this sigma, that is the surface tension, is towards outside. So when we will balance these two forces, P into pi r square, that is pressure into area, this is the pressure force, and sigma into 2 pi r, that is equal to the surface tension force. So by equating these two, we get that P is equal to 2 sigma by R. In case of soap bubble, what will happen? This thing will remain same, this thing will get multiplied by 2 because the soap bubble is hollow from inside. In case of liquid droplet, it is not hollow, it is completely filled with liquid. Whereas in case of soap bubble, there are two surfaces and it is hollow from inside. So that is why it is coming 2 here, because this surface tension multiplied by length, that will give you the force. And what will be the length? That is 2 pi r into 2. Okay, the change in r is neglected here because you can say that this is r and that there will be one more inside which will have a radius little bit less than r, but that is not taken into consideration. That is basically of very negligible thickness, so that is neglected, and we will write it in simply this form, and we will get P is equal to 4 sigma by r. Okay, and if you can also write in terms of d, changing that r is equal to d by 2. Okay, then inside a liquid jet under equilibrium, we say that this is a liquid jet. This is a liquid jet having radius r and length is L. So P into 2r into L. What is this? 2r into L is the projected area. This is 2r diameter into length. That is the projected area. P into 2r into L is equal to sigma into 2L. What is this? Sigma. This is the sigma, that is surface tension. And what is this? 2L. This is one L and this is another L. That is sigma into 2L. We won't consider this line and this line into this addition because we are considering a long jet. We are considering a long jet, a long pipe kind of a system. So we will not consider this thing. We will just consider this sigma into 2L, and from this we get sigma is P is equal to sigma by R. Also it can be again changed in terms of D by taking R is equal to D by 2. Okay. Then another property, important property known as capillarity. What is it? It is defined as the rise or fall of liquid in a narrow bore capillary tube relative to the general adjacent level of the liquid. See what happens. There is a liquid, and if you dip or if you insert a narrow bore capillary tube into that liquid, so the level of liquid in this narrow bore capillary tube may either rise or may either fall with respect to this adjacent level of fluid. That phenomena is known as, or that property is known as capillarity. And the capillarity comes into existence because of the interaction of the forces of cohesion and adhesion. In this case, both the forces of cohesion and adhesion plays their important role. Okay. Then there are two phenomena. One is capillary rise, when the liquid inside this capillary tube rises compared to this general adjacent level of the fluid in the container, or it may also fall. So both these cases are considered separately. One is capillary rise. This is observed when a glass tube is inserted in water. Okay, when this is a glass tube or a narrow bore capillary tube. When this is inserted in liquid, then we experience a phenomena of capillary rise. What happens in this case? The force of cohesion, that is the force between similar kind of substances, is less than the force of adhesion. That means hence the water wets the glass surface. This means the force of adhesion, that is the force of adhesion between the water and the glass surface, is more, so the water wets the glass surface. If this would not have been the case, that the force of cohesion would have been more than the force of adhesion, then the glass would not have wet the or the water would not have wet the glass surface. Okay, then water tends to rise at the point of contact. This is the point of contact, and water tends to rise at this point of contact. So shape of the meniscus. What is meniscus? This is meniscus. This is meniscus. Okay, this is meniscus. This is not a straight line here. This is a concave upwards. This is a concave upwards. Okay, and as a result, the angle of contact. What is this angle of contact? This is the straight line along which the surface tension force will act, and the angle with which it makes with the horizontal axis, with the vertical axis, that is known as the angle of, and that too measured from the upper side, not from the lower side. Okay, please make a note. It is measured from the upper side, and this is the surface tension force acting along this direction, making an angle theta with the vertical from the upper side. That is known as the angle of contact, and as a result the angle of contact becomes less than 90 degrees. This is the case of capillary rise observed when glass tube is inserted in water, and ideally the angle of contact theta is 0 in case of water. Then another phenomena of capillary fall. This is observed when glass tube is inserted in mercury. So in this case you can see that this is the general adjacent level of liquid, and the liquid inside this capillary tube, when it is dipped in mercury, falls. From this level it falls down. Okay, the following sequence of events take place. What are those? Forces of cohesion is more than force of adhesion. So force of cohesion is more than force of adhesion. That means the mercury does not wet the glass surface. So if sometimes the question comes that why the water wets the glass surface and mercury does not, the simple answer is the force of cohesion is more than force of adhesion in case of mercury, whereas in case of water the force of cohesion is less than force of adhesion. Okay, so in this case the mercury tends to fall at the point of contact. This is the point of contact, and at that point the mercury tends to fall. The shape of meniscus will be convex upward. This is a convex upwards, and the angle of theta, this is the that I already told you, this is the direction along which the sigma, the surface tension, acts, and this is making an angle of theta with the vertical axis from the upper portion, and this theta is more than 90 degrees. So the angle of contact theta is more than 90 degree, and angle of contact is approximately around 128 to 130 degree in case of mercury. Okay, then how we have to find out the expression for capillary rise and fall, that how much it has fallen or how much it has risen, that we will find out under the equilibrium case. See, this is the surface tension, okay, sigma, this is angle theta, so this will be what? Sigma cos theta. Okay, this will be sigma cos theta, or you can take it sigma cos theta in this direction also, that does not matter any much. Okay, that will be sigma cos theta, sigma cos theta into 2 pi r. This is the surface tension and this is the length, that is the 2 pi r is the circumference. So sigma cos theta into 2 pi r is the surface tension force, and this force is nothing but the weight. This is the volume, pi r square h, this is the volume of this portion, into rho into g. This is rho into g, and this part, this is h is only this much, and if this part were to triangle that you take, that is not of much concern and that is generally neglected. But if it is specifically maintained, or the dimensions of this part has also been provided in any problem, so you have to consider that also. Okay, please keep in mind this is just a ideal derivation. Do not use it for every case. If in some case these dimension, the dimension of these part has also been provided, so please kindly take them also into consideration. Otherwise, this is the under equilibrium, the concept is same, the weight is to be balanced by the surface tension force. So this is weight, this is balanced by surface tension force. This gives h is equal to 2 sigma cos theta upon rho g r, or this can also again be changed in terms of d, taking r is equal to d by 2. So in this case we see that h is inversely proportional to r, or inversely proportional to the diameter. So when this r or d will be very much less, then h will be very much more, and when this r or d starts on increasing, this h will keep on reducing. So for the tubes of more than 6 mm diameter, the capillarity effects are negligible. Means when this d r becomes more than 3 mm, or the diameter becomes more than 6 mm, then this h becomes very much small. Okay, so hence the tubes of manometers are made up of diameter greater than 6 mm, because in case of manometers, that we will discuss later, in the case of manometers, h, the height is very much important in determining the pressure, and if there are some effects or some rise or fall in the liquid level due to the capillarity effect, then that won't give us the exact value of pressure. So in that case this h should not be there due to capillarity. So for that effect to nullify, the capillarity effect to nullify, the diameter is used is more than 6 mm. So that's it for this lecture. In the next lecture we will start pressure and its measurement. Okay, so if you have any doubt or any queries, any question, you can write it in the comment section below, and your suggestions and your queries will always be welcomed. Okay, so thank you for watching this lecture and have a good day.